by myself will be easier. So I'm Philippe Jacquet from Inria, has been with Nokia Bell Labs during 8 years and working on information theory, telecommunication. And Dimitrios will introduce himself.
Hello, guys. Thank you, Philippe. So I'm Dimitrios Milioris, and I was also working for almost 8-9 years at Bell Labs, and an active member of Links since the first year, I think, and have interests on various problems. But here today we're going to talk about text analysis. I feel that Philippe likes very much, I know.
This is an old topic.
Yes.
So I'm going to. So I'm the one who starts.
Okay.
We toss a coin, and finally I lost. So I will start, and so the presentation will be about pattern matching to follow the one workshop or reading group you have with I think Fabien Mathieu about how Markovian model can create nice-looking words, even if this word that exist. And in fact, all this is a consequence of the science of pattern matching that I will try to describe. So the talk will be in 2 parts, 3 parts, in fact. One part will to present the fundamentals about pattern matching, the Markovian model around pattern matching. And the second part will be an illustration, entertaining illustration of pattern matching and Markovian text generation by Dimitrios. And after I'm going to speak quickly of John complexity, and at the end, if we have time, we'll have a short addendum about the use of pattern matching around the COVID genome. Some new research, since it is in the mood of the time, it's maybe interesting. So if we have time, of course, because I don't want to take too much of your time. So, okay, so the definition, so very quickly the definition, because I think it is something that everybody knows. We consider a finite alphabet, and we are looking on words, finite text written with this alphabet A. For example, it could be a binary alphabet, but it could be an alphabet of size 26 or 30, if you include all the letters in Latin plus the punctuation. Some convention, a text W is a factor of another text X if basically W is inside X, but without any separation between the symbols. For example, the example, you have ABBA, which is a factor, and can find ABBA in the text X. The pattern matching problem, it's a whole problem in computer science. It's given a factor W and a text W and a text X, determine if W is a factor of X. And this is an old problem. The application is parsing, compilation, search, addition, compression, and so forth. So it's an old problem which has already old and very good solution. For example, if you have a factor, you have W, and you want to check on a text of size capital N, the naive algorithm is to check all position. Therefore, the complexity is the product of the size of the text X and the size of the factor. And there is an old solution, which is a non-backtracking algorithm, which costs only the sum of the length of the text, and this is the algorithm of Knuth Morris Pratt that I'm not going to describe in detail. And to cope some confusion that occur very frequently when we discuss about factors in a text, you should not confuse a subsequence versus factor. A subsequence is a sequence of symbols increasing in increasing positions, but they can be separated by other symbols. The example, for example, you have ABA in X. There is a subsequence ABA made of symbols which are not contiguous. So all factors are subsequences, but the reverse is not true. And there is in dynamic programming, there is a classic algorithm, the Hunt-Zimonsky algorithm, which computes the largest common subsequence between two texts X and Y. All students have to work on it, so I'm not going to discuss it. And also, we are going to discuss about some aspect of information theory. Information theory means that you need some probabilistic model and sequence. First, we take the simplest of all model. All the symbols are selected independently, randomly. It is called the memoryless source, because there is no correlation between two consecutive symbols. The probability of text is a product of the symbol probabilities, and the number of occurrence of the factor in X, you have just to check every position, and the average number, the probability that one position start the factor W is PW. Since you have n minus the length of W position, because you cannot go up to the end, you have to end short to the end. And if W is a sufficiently small size, then basically the average number of position is the size of X times the probability of occurrence of factor W. In the probability of occurrence of factor W in the model of the source X. You have to be careful that it is not the model of generation of the factor W, which is just given at the very beginning. It is a model of generation of the text X. There is an extension of the word sequence matching problem, which is when you have a sequence of different words. And so you have a sequence of different words, W1, W2, WK, and you have a sequence, text X, and you want that the WI be factor of X and appear in this order in X. Basically, you can find W1, and then you jump W2, then W3, and so forth, so forth. Or there is some twist if you allow overlap and not overlap. It is not important for our problem. And the average number of such occurrence in X, how many tuple of position you have this matching, is given by this formula. The formula is basically simple to understand. You have to select K position inside your text X, and then to ask if this position contains start factor 1, second position factor 2, third position factor K. You have here, it is in the case you don't have overlap, otherwise it is a little more complicated. And when basically the span of the factors are negligible compared to the length of the text, you have this formula that basically it is the size of the text power K and the product of the probabilities for each factor. If the order is different, well, it's very simple. You have to multiply by factorial K, and you get this expression. We'll look This will be useful later at the end of the talk if you arrive to this this place when we are going to talk about matching over COVID genome. We can extend the problem of matching on sequence are no longer a set of labels on an oriented chain. In fact, a sequence is a set of labels on an oriented chain. You can extend it to set a label on lattice. So as if you consider your problem instead of in dimension 1 is dimension 2 or dimension 3. You can have more complicated elementary graph. And Markovienne will understand the application. I will discuss this later. In the multidimensional pattern matching, you have to be careful. It looks as simple as one-dimensional pattern matching, but it's not as simple because your factor W may have a convoluted shape. And this complicates the pattern matching algorithm. This is another story. And we will now concentrate, with some rare exception, on the linear sequences, the text. One usage of pattern matching. This slide is a little longer than the other, but basically, this slide wants to explain what is a predictor in information theory. You have a sequence, finite sequence, or you have a truncated sequence. You have a semi-infinite sequence, and you truncate it, and you want to guess the next symbol. Assume, for example, that the sequence is the weather. Since we consider that the weather could be something good weather, bad weather, good weather, bad weather, so it will be in a binary alphabet. And you want to guess the next symbol, xn plus 1. And you want to minimize loss, basically the probability that you fail. And if we consider a memoryless model, the optimal predictor will always predict the same symbol, the symbol which occurs the most likely, which has the largest probability. It's, if you want to predict the weather in Greece, the most likely weather is nice weather. So you will have always the prediction will be nice weather, even if it rains from time to time. Otherwise, the optimal is more complicated. You have to consider, given the past, the sequence of symbol before xn plus 1, you want to know which is the most likely. And of course, this will change if we describe the sequence one by one, because if you don't have a memoryless sequence, there is an effect from the past weather on the future weather. An asymptotically optimal predictor is when basically the probability that you don't find the most likely symbol tends to 0 when n, the truncation position, tends to infinity. There are many predictors, but most predictors you need to have a model. For example, you need to have a model of the weather to predict the weather. A predictor is universal when you don't need a source model. That basically it will adapt itself to find the optimal answer. The nice picture on the right is Nostradamus, which is a father of predictors in information theory. Pattern matching gives the possibility to build an asymptotically universal predictor. You text the algorithm is as follows. Is simple. You text the text. You look at the largest suffix W. Suffix is a factor which is at the end is every factor which ends at the end of the text. So it is just a truncation of the end of the text. So it takes the largest suffix which has a copy inside X. You may have several copies if the alphabet is greater than is binary, greater than binary. You may have several copies, and so here you could say, okay, this, if I consider that my sequence is an stationary, I could take the next symbol of this copy and to say it and to decide it is the prediction. But this won't give you the most likely because you have only one element. So in order to increase the number of elements and to have some choice, instead of taking the copy of the largest suffix, you take the copy of the half of the largest copy. And then in this case, you have many more copies. And there you take the next symbol after each copy, and the prediction is the most frequent symbol, most frequent marker. We call the next symbol after the copies the marker. So you have the universal predictor. A predictor, we don't know yet by definition at this stage that it is universal, but we will show in which condition it is universal. It is universal in the case when the sequence is stationary, so it means that it has a probabilistic model on it, and the probability doesn't depend on the translation on the text. And that it means to be exponentially mixing. Exponentially mixing means that basically you take two events for a probability. What is the probability that a factor at some position U and factor at position W has some properties. And in fact, the joint probability of this event has a correlation which fades when the events are far apart. That basically the events tend to be independent. Therefore, it is a product. And the correlation is exponentially decreasing. So the correlation exponentially fades. And this is the definition of exponentially mixing source. We will see some example of exponentially mixing source, which will be the Markovian source, but there are others. And coming back to the problem of the pattern matching predictor, the predictor have described, you have the number of half copies of order square root of the size of the truncated part of the sequence. So it tends to infinity, and this is crucial in order to have the fact that we have enough sampling of the next symbol to find the most likely symbol. The problem here is that I see all this face, but it hides my screen. Okay, but it's not a problem because of the face on the right is Markov. So now I'm going to very quickly describe the Markov chain. What is the Markov chain? I know everybody knows, but just to fix the notation. So you have, it is a distribution with memory, contrary to memoryless source that we have described before. It's you have a memory. In this case, it means that the next symbol depends on the previous symbol, only the previous symbol. You don't need to know all the symbol before. So it is the definition of the Markov chain, and precisely the transition between xn minus 1, so the previous symbol or the next symbol, is given by a matrix in the A to A matrix, A meaning the size of the alphabet. And all the symbol xn, xs plus 1, and so forth depends only on the previous symbol. You can forget the other symbols before. So very quickly, you know that there is a stationary distribution, which is the eigen vector of the transition of the transition matrix, because the first main eigenvalue is 1. And we know that if you want to know the distribution of a symbol at the nth position, it's given by the iteration of the matrix and the initial distribution, and it converges to the stationary distribution exponentially fast, where rho is the second eigenvalue, which is of modulus smaller than 1. And the consequence is that the correlation between past and future exponentially fades, so we have an exponentially mixing model. And we have this property that the exponentially mixing, and remember, we have the equality when it's memoryless. As something which is important, but not for our problem we are described, but there are many errors in literature, in algorithm, in information theory, that the past affect future, that we all know. It is the property of Markov, Markov source model, but also the future affect past by definition. It's probabilistically. If you fix one symbol, there is a dependency on this symbol with the symbol before. If you fix one symbol, therefore the past and future become independent. Of course, and then it will be the introduction for our games. Not yet. This is, we can have Markov chain with longer memory. That instead that we depend only on the last symbol, we depend on the last factor of length r. Therefore, the chain is initialized by a word of length r. R equals 0 means the memoryless. And we have all the property that we have a mark, because we can see that as a Markov chain of memory 1 over the Cartesian product, R Cartesian product of the alphabet. Therefore, the matrix P is a matrix in this Cartesian product. And we have the same property with the Markov of memory 1. With a difference that we have to consider factors instead of symbol. A side remark, this is absolutely useless, but I'm happy to tell it. You can find multidimensional Markov chain on the same model of sequence of lattices. You can find Markov not chain. It is no longer a chain because it does not have a past and future. It is a little more complicated, where basically the symbol of one node depends on the symbol, for example, in this case, above, on the symbol on the left. But there is many complications. For example, the probability of such a symbol sequence is not the product of transition. It's more complicated. The reason because to arrive to one symbol, you have many paths. So you have, in fact, many complications. It looks simple view from far, but in fact, when you look closer, you have many complications. Pattern matching can be used also for compression. That is one of the most fundamental results with pattern matching. It is one of the first universal compression algorithm. So the compression, it is just mapping a text X and alphabet A into a binary code BX, such that eventually the size of the compressed code BX will be smaller of the size of the original text. Of course, in this case, you have to make the translation in binary. And there is two kinds of compression. There is a lossy compression, and there is the lossless compression. The lossy compression is when you get something. Basically, what is on your screen, it is a lossy compression. Lossless compression, and then there is a reverse mapping. In this case, it is more text. For example, you want to send a text, you want to store a text, so you don't want the text to be affected by the compression. You want to be able to recover it. The compression and prediction are related problems. They are related. Every time you talk about compression, every time you talk about prediction, there is some ping pong between the two concepts, but they are not equivalent. For example, you could imagine that you can compress by indicating only the position where the prediction failed. And in fact, it won't work well because you will have too many failure, and this will give you a too large binary code. The compression is optimal when the length of the text of the compressed code is the entropy. In fact, the entropy is the absolute lower bound of the compression. You cannot do better. The reason for that is because there is this reverse mapping. Therefore, the entropy of the compressed code should be equal at least to the entropy of the original code, and the entropy in this case will be the length of the code. In fact, it's a little more complicated, but basically the entropy is the absolute lower bound. Now, the universal compression based on pattern matching is a Lempel Ziv or Ziv Lempel, it depends. If you read from the right to left to right. In 1977 and 1978 are two algorithms. And the principle of the algorithm is that it produces CX, BX, it's a list of tokens. And the compressed code is a list of tokens. The token is either a new symbol or a tuple, which is a position and the length of a factor. The position of a factor, the length of a factor. On the decoding is you read the token list. If the token is a symbol, you append the symbol to your current text. If the token is a tuple nm, you go to position n, and you take the factor of length m at position n, and you copy it, and you add it at the end of the text. Therefore, it is strongly related to pattern matching, and in fact, to the algorithm that I was not going to describe how to build the list of tokens is the pattern matching algorithm. For example, look at this example. It is a universal compression. Look at example AB. It will be encoded in A, B, B, and after the fact that the sequence AB is repeated 11 times. And you can see that if we have used the first algorithm for compression by Shannon and Huffman, you will have something much larger. You will have basically to repeat the symbol A and the symbol B several times. It will be 0, 1, 0, 1, 0, 1. So there will be no compression. The Huffman encoding is good for memoryless, but not good for Markovian. This is an example of text with a Markovian strong correlation, and you won't be able to detect that there's repetition. Now to look more at the performance of this algorithm, we call the entropy rate basically the ratio between the entropy of the text and the length of the text. And we consider that it is basically when the text increases, it tends to be constant, to simplify. And using analysis of algorithm, scientific analysis of algorithm, we find that the average length of phrase, basically when you have a text and you want to see what is the size of the largest copy of it, when you have just a prefix of the remaining of the text, you want to find which one has the largest copy in the body of the text. you have the length of the phrase, basically that will be used for the token, and it is asymptotically equivalent to the logarithm of the size of the previous part of the text and the entropy rate. Therefore, the token is encoded. If you forget the initialization when you have the symbol you never met before, therefore in the beginning you have this symbol. In general, Lempel Ziv use a database. You don't declare the symbol. Therefore, a token, the most frequent token, the NM token, is encoded into something which is log of to the length of the text. It is n. It is a position inside the text, so it is in log of n, and log of n, log of the length of the text, and the length of the phrase. In fact, the length of the phrase, since it is of a size equal to log x, it will be log x. Therefore, the code length is asymptotically equivalent to this, the length of x times age. So it is asymptotically equivalent to the entropy of x. In fact, it is entropy of x plus something. We call this something the redundancy. The redundancy, the larger the redundancy, the worse is the compression algorithm. So the issue is to reduce the redundancy part. But anyhow, if you look only to the asymptotic equivalent, Lempel Ziv is asymptotically optimal. Now I'm going to introduce very quickly the generation of text, the Markovian game. And you take an original text, X, that you ignore, you hide it. You train on it. Training a Markov matrix is very easy. You just have to enumerate all transitions of memory R. And from this Markov matrix, you produce via random generator, random text XR on same length. And the game here will be to see the evolution of the entropy rate from the memory R equals 0 to the memory of 3, 4, 6. And also, which is the most the funniest part, is try to guess X from XR. Now, I try. This is a text, and you simulate it in memory 0. And you see that the entropy rate is relatively important. It's 3. Is there anybody who can guess the text? No, I don't ask because either you already no, you are not allowed. It is impossible to guess it. Memory 1. Memory 1 is interesting. You can discover that at least it is a text in some language. You can even guess it is something close to Latin. Memory 1. Only one symbol of memory. The entropy rate is reduced. Memory 2. Already you know already that it is French. And you have already again a drop in the entropy rate. So now I think everybody has guessed. In order to avoid that everybody unmute their microphone and produce a disaster, I will go directly to the end. Memory 3. Memory 3, you can see there are words that are not existing, but you can guess what is the text. But you have words which don't exist. Subsisterité, it's a nice word. It's like some medieval word. Memory 4, and then the entropy. Here there is no way to everybody who go to school in French in France and know this text, and it's not okay. Therefore, now I give the floor to Dimitrios, and you will play. But I don't know how we can organize because otherwise.
But you didn't say which text that was.
Ah, the text. It is la cigale et la fourmi of Jean de La Fontaine. I'm very proud of this.
So can I share?
Yes, please.
It says that you have to stop sharing first.
Good, you tell me.
Yes. Okay, so let me share that one.
Of course, Gerard don't have the right to participate because he participates to the elaboration of the game.
Yeah, so that was designed, as you can see, with the old logo of Alcatel-Lucent on the right.
Is there something to win anyway? Otherwise,
yeah.
So maybe I will participate.
Yes.
So something to win.
The idea was that. Sorry.
A parachute.
The parachute, yes. So the idea was that you choose a singer from the left side, and then there are a few songs which randomized appear. So we pick randomly one. And then we simulate at each step from like 1 to 10, the Markovian order. And there's something that I cannot share right now due to restrictions from Zoom, but there is this thing that Philippe put there as, becoming an expert or having, let's say, having a telepath or, I don't know, there are a few things that I don't understand, but okay, but the last one is ça serait plus facile avec la musique. Okay, this I understand. So let's try then one. So who is gonna play? Let's do it interactively, Philippe, together, I guess.
Yeah.
Okay, so which one do you?
If it is with me, you have to take an old timer.
Okay, Charles.
Yes, Charles. Yes, Charles. Because I think I'm the only one to know this.
Okay, so that's what you get, and then as you start increasing the order, you can see, like, for example, with symbol like the tuples, second one. So as Philippe showed in the early one, things start appearing to have a meaning. A third one.
Which is funny that I don't remember.
Very good. The fourth one. The fifth one.
You are the one. You are the one. You are the one.
Let's see. Incorrect.
Yes. Or maybe.
C'est pas Formi Formidable le titre?
Formi Formidable.
Okay. Very good.
And the answer is the score. The answer is given by the John complexity that.
Yes, this I wanted to show. Maybe I can. So yeah, there is a comparison we can show later, actually, for the analysis of factors of the title and the original title, and then the guess based on the common factors that you have between the two trees based on joint complexity. Okay. So should I stop sharing?
I just have a question. Sorry.
Yes.
Speaking.
You want to play?
Yes, Ludovic.
Yeah. So I understand that you have a matrix of probability transition.
Yes.
On symbols or given tuples of symbols.
Mm-hmm.
But this probability, do you learn it on the same text and only this text, or more larger corpus?
No, this one is based on the specific text.
Yes, so you only learn what could happen on the text itself.
Mm-hmm.
Okay.
Yes.
This is what I suppose, but I wanted to be sure. Okay.
Mm-hmm.
That's okay.
Yeah.
Ludovic can play.
Yes, you can play, Ludovic, if you like.
You have asked a question, you have to play.
Yes.
I'm bad at this kind of games. I don't know the titles of the songs.
I have the same problem. Also, we repeated before.
For example, the Song of Aznavour, I knew it, but the title, I didn't remember the title.
Okay. Okay, stop share from this. Philippe, can you put back the slide?
Okay, so you don't. Okay, so put back the slide.
You
So,
you could have tried another one just to see what happens.
Yeah,
yes.
as you like.
Yes, try another one.
Let me try then again. Show.
Just
Michael Jackson, for
Michael
example.
Jackson in English.
Yes, okay. So it's easy, as you can see.
Yes.
First, second, third.
You are not alone.
You are not alone.
Who said that?
Marco?
Yeah.
Okay. Very good.
Oh, he's very good.
I train for I want to participate to N'oubliez pas les paroles.
It's kind of, at a moment we wanted to see we could not have a game like that and sell the game.
Yes.
But you need the music.
Okay, stop share now. And Philippe, if you can please put
Okay.
back the slides.
Yeah, it would have been nice if you had done the same with the music, actually. To
That's a good question.
reconstruct the music. The
That was a very nice idea. We were thinking about that actually at some point.
Yeah, yes. That's a good idea. That would be fun. But you have to be careful because the result will be horrible at the very beginning.
Okay.
So I continue.
A question about how you implemented it.
How what?
I mean, how is it possible by building the Markovian model to reproduce the final text with the exact series of words? There's something that you are doing there, right?
So you have the probability of a symbol to follow any other symbol based on the text that you have.
Right.
And then of a symbol following any other two symbols continuously. Right. And then a probability of a symbol following any three, etc. So if you pick any random, so if you have these kind of probabilities and you go and you pick randomly the first letter, then it starts
factor,
yes, and then it starts adding up as you go for let's say the rank 1, 2, like 2 following 1, 3 following 2, 4 following 3, etc., etc. Right. So at the end you have a limit. Let's say that a word, the biggest word of your text is like, I don't know, 10 characters. So if you go to 10 and you add also the space, yes, and everything, then you have actually all the sequence generated.
Right. So you initiate always with the first letter of the. You
can start with the first letter.
The first symbol.
The first symbol. Yes.
You don't distinguish the letters and the symbol.
Yes.
The comma it is considered as a symbol.
So you start.
You can overlap two words, for example.
Mm-hmm.
Okay.
It is not the generation of words by itself, a generation of text, and you have the insertion of punctuations.
Mm-hmm. Exactly.
And so your initial, let's say, symbol is the initial symbol of the song, always, be that one letter or be that 3 letters. Otherwise, you would start by random symbol, and maybe you would not.
No, if you start with a random symbol, one thing that you can do, I have tried that, you can have a circle, and then you basically start the song from a specific point.
Yes, I see.
And you go around. If you give the first letter of the song, of the whole sequence, because it's a whole sequence, then you have at the end of the 9th or 10th, the whole...
okay, this answers my question. Thank you. Yeah, great.
You're welcome.
I have a question. Do you hear me?
Yes.
Okay. Yes. So is it possible to add some context to this Markov? Because, for instance, if I see the word pick and I see that 4 lines before in my text there was the word Markovian or Shannon or whatever, I know that maybe after pick I will encounter symbol. if instead I see the word pick, but 4 lines before I saw the word supermarket or grocery, maybe the word after pick will be apple. So should I necessarily train 2 different Markov chains in these 2 contexts? Or is there a way to take into account this interaction between far away words that give me a...
complicate the model as much you would like, but the beauty of this, in fact, you don't need something complicated to have to have a creation of text which looks really like the original text. In fact, when you do that, you see that the context of the word is well embedded in the context of the original word in the original text. Of course, there will be huge modification, there will be repetition, there will be loops, but you don't need to complicate. That's the beauty of this game, is the fact you don't need to have a complicated model to generate a text that looks really like text. We use, I remember we used that on
books.
Lot on many texts of the European
books,
Commission, for example. There's a lot of entropy. The text of our CEO, for example, I remember we used it, and it was possible to recreate a speech of our CEO without noticing a significant change in the meaning.
Okay.
So I will go to the last part.
Yes, I would say if we skip the joint complexity thing, and if you want to show the
the
COVID and
again, there is a mention of the joint complexity. I will explain it very quickly. Yes, what very useful, something which is very useful for when you do pattern matching is suffix and prefix tree. It is a data structure. Instead, the secret to avoid to check every position if there is the symbol W and how many times it occurs, there is one simple way to do that. It is to build a tree structure of all suffixes or prefixes of the text. And in this case, it is very easy to find if you have a sequence W, a semi-infinite sequence W, to find the largest copy of it inside the text X by just exploring the tree. And the computation of the suffix tree is in X log X if you use a naive algorithm. It's basically to insert all consecutive suffix. You have the Rissanen algorithm, which makes it linear. It's kind of more sophisticated than the kind of equivalent of the Knuth-Morris-Pratt, but in much more sophisticated. There's many pointers. And the search in tree, as we see, it's just a depth search. It is in log X. And there is an extension for multidimensional matching, which is called the graph trie, for which there are applications. For example, you have a log of alarms in a network. A network is a set of objects connected in a graph and spanning in time. And you can describe all the sequence of alarm as a graph trie. And this is a convenient structure to find a repetition, to make prediction in almost real time. The joint complexity that was mentioned by Dimitrios is basically you have two texts, and you want to see if the texts are talking about the same or not the same thing. But you don't want to have something very complicated. You don't want to do classification of short text. And one way to make it very quickly is to enumerate a number of common factors within the two texts. You know what is a factor in a text, a factor in another text, and you want to know the number of factors that are common to the two texts. But for example, between the two texts, here the joint complexity is 25. And if you take the assumption that when two texts are on the same topic, then the joint complexity should be large. Therefore, it's a very fast way to make classification of tweets, for example. And contrary to natural language processing, you don't need to know the language, the grammar, the vocabulary. It is resilient to misspelling, and it is less efficient than the artificial intelligence system based on deep learning, but it doesn't need any training. Therefore, you can do really a very quick classification without training. And for example, for Twitter, this is important because you may have trends that appear very quickly, and there is you don't have time to train a neural network on this new topic. So the joint complexity can basically take the lead until the deep neural network converges. Ah, no, this is my, I see, this is a copy. This is me, you can hear me again? Oh, okay, what is it? It is describing.
Philippe?
Philippe?
You hear me?
Yes.
Perfectly.
Yes.
You hear the recording? Because I forgot to remove it.
No, no.
You don't hear it? Okay.
We only hear you.
Very good. So I can ignore what is the recording. So basically, the idea was to take 5 topics: politics, sport, technology, economics. You have 10,000 tweets, and you take all the tweets that contain the word politic in one set, all the tweets that contain the word sport, all the tweets that contain the word technology, all the tweets that contain the word economics, and all the tweets contain the word lifestyle. So you will basically collect between 1 or 10%, depend on your sampling, of the tweets. The challenge, how to classify the other tweets which don't contain these words, these specific keywords. And for that, you use joint complexity. You try basically in the database we have built from the tweets that contain the original keywords. You try to find from one tweet that contains this keyword, which one inside this set is the closest. And you put it in the database. And at the end, it will classify the tweets according, eventually, to the keywords. So now this is the topic, the tweet we have captured, and which does not contain the keywords. And the matching is relatively good. It's not 100% perfect, but it is relatively it's a good matching. This technique has allowed us to get the third prize in the SNOW project. The challenge was to listen to Twitter during one day on specific source and to make a classification of the trends and to give the most frequent trend and to display one headline per trend. And we get the third prize. And in fact, they told us we could have gained the first prize because they didn't know that we were using such a simple algorithm. And in fact, it is relatively efficient. It was not the tweets that was tracked for the challenge. And it can capture tweets written in other language. It is that the classification is less accurate. The reason for that is because these tweets in different languages were less frequent in our sampling. But for people who understand the language, the classification is relatively accurate. You can ask why it is possible to make the joint complexities. In fact, all these languages are written in ASCII. So in ASCII, you can make the pattern matching. We don't. You are not blocked by the fact that basically the alphabet is different. And also, what is very efficient is to be able to detect a sudden trend. Last year in September, there was at noon an explosion, a loud explosion. Nobody knows what happened, but I used the beautiful trend searcher of Dimitrios and Gerard to ask who have heard this explosion. So I entered the keyword explosion. I entered my city, it was around Versailles, and I got all the most significant tweets that fit the best the query with where there is a loud explosion in Versailles. It was in French because it was in Paris, and I collected a lot of tweets, and it was easy to see that everybody heard this blow, and if everybody can hear a big blow, but they are very far apart, it means that it is a sonic boom. So I was able to detect to tell my daughter that it was sonic boom, and she was very impressed. So I got the master daddy for at least 2 minutes. I was very proud. The theoretical performance of joint complexity with Markovian model. Basically, the joint complexity of two texts of same length is smaller than the length of the text. It has this complicated formula, but basically it is x to power kappa, and kappa is strictly smaller than 1 when the sources are different. When the texts are different length, but from source with same parameters, then we have a more accurate formula, which is this formula that the joint complexity is basically a kind of entropy-like formula. If you see the log of x plus y minus x log x minus y log y, it is like an entropy-like formula divided by the entropy rate of the text. If you want some self-promotion, which is necessary. All this beautiful publication summarize all this theoretical analysis and results. And now, if do I have still some time?
5 minutes.
5 minutes? Oh, this is far too much. So, can you recognize this guy? So it is a question, and I'm not expecting an answer because I have only 5 minutes.
It's the COVID virus.
Yes, you recognize it. Yes, this is COVID. It is a sequence of stupid COVID. That is a sequence of SARS-2. And now you can find the sequence. There is a database with many genome sequences. The genome sequence is a sequence on alphabet 4, of size 4, and you can play with it. So one thing, for example, we said that the COVID is coming from the bat coronavirus, and I made the pattern matching, the joint complexity of for particular reason, I make from the right to the left for particular reason. So I compute the joint complexity between the suffix, the suffix of this COVID sequence compared to the BAT1 coronavirus, and I compare with the pure random case, and we can see that actually the COVID has joint complexity with BAT coronavirus, which is above what we expect if they were unrelated, purely random. And you can do the same with another. Now in this case, I normalized. I divided by the average theoretical. We had the formula that I displayed 2 slides before. And I compare with HIV, HIV genome, another ugly disease. And you can see that there is the SARS-2 is related with the BAT, but not related. You can see that the joint complexity is below the average, not related with the HIV. Despite this, there has been a controversy. I don't know if you have followed that. There was some accidental claim that was accidental insertion of HIV sequence in SARS-2 genome. Indeed, they are not related, but you can find, I just checked, you can find 19 short common sequence of HIV in the SARS-2 genome. And each factor of the size 20, more or less 20. The 20th one is the BAT coronavirus. And this was a paper from Perez and Montagnier. So a paper you can find. It has never been completely published. It is difficult to understand. And here I display the computation by joint complexity. I cut the genome of the COVID in a slice of size 20, 30. And I compute the joint complexity with the other sequence as a whole. There's a sequence 1, sequence 2, sequence 3. There are 19 of them. Sequence 20 is the BAT. And at every time, I take the maximum of the joint complexity discrepancy, but with the standard deviation. So therefore, how far you have a joint complexity which is unexpected. This is a multiple of the standard deviation, which is larger than 3 or 6. And there you can find the position where this accidental insertion are located. And if you take the formula for the probability for such accidental insertion, it is a word sequence problem. You take the formula of the word sequence problem, you have 19 factors of size 20. The probability to have one matching, if you assume it is something uniform, would be 4 to minus 19. And if you take the formula, you get probability which will be 10 minus 144, which is absolutely negligible. Therefore, the conclusion of Perez-Montagnier was to say, this virus has been forged by evil people, evil scientists. They have just inserted some pattern of the HIV, which are not related sequence. And this has been an error, and we call that a chimera, and it has been escaped from hidden lab. Indeed, if you take instead of taking the COVID genome, you take the reverse, you see that all the matching, all the crazy extra matching disappear. So now, in fact, you can change them in perspective. So you know that it's a controversy that there is still a discussion. People are not believing or believe that this virus has been built in a lab. I don't have any answer for this, but I just make a change in perspective. If you unfix the matching factors and you unfix the sequence will match with COVID. In fact, Perez and Montagnier extracted the sequence from the monkey, the HIV1, HIV2, and also the reverse of them. So you can assume that you have a corpus of 10 to 5, 10 to 6 base. And now what will be the probability to have 19, at least 19 matching? And you see in this case that the probability is not that small. If you forget about error, you have something which is a 10 minus 4. And if you allow errors, that is basically the case, then there are never matching perfect matches. There are some which are perfect, but most of them have errors. And with for maximum of 3 errors, you multiply by this binomial, you get to a probability to have 19 matching of 0.16. Therefore, it means that you can have this. If I don't know how many sequences they have tried, but it's funny that they have tried a sequence from the monkey, from the HIV1 and 2, and reverse. In fact, you can see that if you consider the matching sequence, you compare them. They have also a lot of accidental matching. Basically, they are not independent. You have matching also between the matchers. And for example, I took the segment HIV, complicated HIV2. The only thing that I know that it has been extracted in 1993. Therefore, the technology to create it was not existing in 1993. So basically, I don't have any definitive answer because this is not a game of pattern matching and gene complexity and COVID on the genome, but there is something that you can have some idea that sometimes the matching are not that infrequent. So, but what is I detected there is an excess of pattern matching, which was there was in November 2020. One article was describing a novel bat coronavirus discovered in Yunnan, which was closely related to the SARS-CoV-2. And I don't know if you remember, the big issue is to say that to prove that the COVID is coming from bad coronavirus, and it was kind of a very important statement that has not been created. But here is basically it is too much. You see that the correlation are too strong. Indeed, if you look at the pattern matching between the COVID sequence and this bat coronavirus 2, you see that there are too much. It is basically kind of copy-paste. There are some errors from time to time, but it's kind of copy-paste. And I have not had a large experience, but in general, when there are mutated sequence, the matching are not that big. It is just 2 times the average case in random. Here it is 40 times the average case. So this bad coronavirus 2 is kind of suspicious. Because it's supposed to be a copy of the COVID, but after a lot of mutation that come back to the to the bat, or in general, you have a lot of mutation. Here, it is a comparison between HIV1 and HIV, just a segment of it, and there are mutation, and basically you can find excess of pattern matching, but not that much. That's all, and stay healthy and happy to.
So thank you, Philippe and Dimitrios. Any questions?
I have a small question about the universal predictor. Maybe I missed something in the definition, but if I remember well, you said you picked the largest W suffix in X, which is included in X, which is actually X.
Copy inside.
Yes, but X is a copy inside X, so you would pick X, no?
No, the suffix which has a copy inside X.
Okay. And the copy does not overlap.
Will have a copy inside. It can
Okay,
overlap,
okay.
by the way, but
Okay.
make it clear, make it not overlapping.
Okay.
I'm sure you are fed up of this image.
Other question? So thank you, Philippe and Dimitrios. It was quite interesting, and I really like the end part about the COVID and the genome. It's I think it is quite interesting, at least for me, for my interest.
Thank you.
Thank you.
Thanks.
I will stop the